All right, let's dive in. Today, we're heading into a place that's, well, it's one of the toughest industrial environments on the planet, a cement plant. But we're not going to focus on the giant crushers or the blazing hot kilns. No, we're looking at something you can't even see. The massive, invisible network of air and gas that is, without a doubt, the plant's true lifeline. And we're about to find out why one little hiccup in this system can bring the entire operation to a grinding halt.
So I want you to think about this for a second. If a cement plant were a living, breathing thing, what would be its circulatory system? It's not water, it's not oil, it's actually the gas. We're talking about thousands of tons of it, superheated, packed with dust, that has to move perfectly from one part of the plant to the next. This isn't just a bunch of pipes, it's a dynamic, high-stakes, high-pressure network.
Yeah, so this hidden network, it's just this constant, massive river of hot flue gases, process air, and really abrasive dust. This stuff is the absolute lifeblood of production, and it's on a very, very specific journey right through the heart of the entire plant.
Okay, so here's the journey that gas takes. It all starts in the kiln, right? The hot gas moves through the preheater and the cyclones. Then it gets to the really crucial pollution control stage, the bag filter or the electrostatic precipitator, which are basically the giant lungs of the plant, cleaning out all the dust. From there, a massive ID, or induced draft fan, pulls it all through before it finally goes out the stack. And every single step here is a critical handover, kind of like a relay race.
But what happens when that relay race gets messed up? When the pressure in the super finely tuned system starts to go wrong? And you can probably guess, this isn't a small problem. A failure in this invisible network can have massive plant-stopping consequences. Let's break down what that actually looks like.
The first whisper of trouble? It's a tiny change in pressure. Just a small, abnormal reading that could mean a blockage is starting to build up from all that dust, or, just as bad, that there's a dangerous leak somewhere in the system. It's like the system's check engine light is starting to flicker.
So what happens if you miss that flicker or ignore it? Well, it almost always leads to an unexpected shutdown. And I want you to picture that for a second, bringing an entire cement plant to a dead stop. The cost, the disruption, it's absolutely astronomical, and all because of a problem in a pipe you can't even see.
And even if you manage to avoid a full shutdown, the plant is just bleeding money. See, blockages and leaks make it harder for the gas to flow. That forces those huge ID fans to work way, way harder just to move the same amount of air. What you get is this huge spike in your energy bill, just eating into your profits every single minute of the day.
And then there's the big one. This whole chain reaction has another really serious outcome. If the gas isn't flowing right, those dust collection systems, the bag filters, the ESPs, they just can't do their job properly. And boom, you're suddenly violating strict emission standards. We're talking heavy fines, legal headaches, the whole 9 yards.
Okay, so you see the problem, right? Just waiting for things to break is not a strategy. It's just firefighting. The real key here is to get ahead of the problems. With effective monitoring, you can transform your whole maintenance approach from reactive and costly to proactive and strategic. It's really about taking control of that invisible world inside the ducts.
So, what are we trying to achieve with good monitoring? Well, the goals are pretty straightforward. You've got to maintain a safe draft and flow. You need to catch those blockages and leaks super early. You want to monitor the health of your filters so you know when they need attention. You want to optimize your fan performance to save a ton of energy. And of course, you have to ensure you are always in compliance. It hits every single problem we just talked about.
So the big question is, how do you actually get that kind of control in an environment that just destroys regular equipment? You can't just stick any old sensor in there. You need a tool that was specifically engineered for this challenge. And that's where something like the ROCKSENSOR RP100 comes into the picture. It's a tool built for exactly this job. So what is it? Put simply, the RP1001 is a differential pressure transmitter. All that means is it measures the tiny difference in pressure between 2 points in a duct. And that's the exact piece of information you need to know if your gas is flowing smoothly or if something is starting to go wrong. And the key thing here is it's built to survive in places that would chew up and spit out ordinary sensors. Okay, look at these two specs, because they tell you everything. First, that measurement range, it can pick up on the tiniest, whisper-faint changes in pressure, but it's also tough enough to handle huge system pressures without blinking. Second, look at the stability, plus or minus 0.15% over 10 years. That's insane. That means you can pretty much install it and trust the data it gives you for a decade, which dramatically cuts down on maintenance.
So you have to ask, why does this thing work so well when other things fail? Well, it all comes down to its core design. It's because it wasn't adapted for the job. It was engineered from the ground up to deal with the crazy heat, the constant dust, and the wild pressure swings that are just normal life in a cement plant.
Let's look under the hood. It all starts with this high-stability silicon sensor. That's the heart of it. That's where that incredible long-term accuracy comes from. It also has excellent overload performance, meaning a sudden pressure spike from a process upset isn't going to kill it. And finally, you see all those certifications, ATEX, CE, SIL. Those are basically verified third-party stamps of approval that say this thing is safe and reliable enough for the most critical jobs.
And this is where the magic happens. You put these things in all those critical spots we talked about earlier. You mount them on the kiln exhaust ducts, on the inlet and outlet of the bag filters to see how they're breathing, across the main ESP ducts, and of course to keep an eye on those vital ID fans. It gives you a complete real-time health chart for your entire gas flow system.
You know, when you boil it all down, it comes back to this one simple idea. Proper pressure monitoring ensures smooth gas flow, efficient dust collection, and compliance with emission standards. See, it's not just some nerdy technical detail. It directly impacts the plant's profitability, and honestly, it's right to even operate.
So, this all leaves us with one final thought, especially for anyone who runs or works in a plant like this. You can see the kiln, you can see the grinders, you can touch the equipment. But can you really see what's happening inside those ducts? The question is your plant's actual lifeline, that critical airflow, truly under your control?